Actually, last class, we introduced the concept of asynchronous circuits when you have feedback loop, but you don't have clock. Still we have feedback loop, still we have memory, but we don't have clock. So clock was for synchronization. So synchronization gonna be a little trouble. So we need to deal with glitches and try to find like hazards, static hazards or dynamic hazard. We're going to talk about that today. So today we are focusing on how to find actually output in asynchronous circuits based off input and based off previous states. And we're going to talk about hazards. We already talked about hazard before, but specifically we're going to define what is hazard and what is these glitches and unexpected changes that happen. Sometimes hazard 0, hazard 1, it depends. If the level is 1 and suddenly go to 0, that's hazard 0. We're going to talk about that. Also, we're going to see how we can find hazards. Like for example, in D flip-flop or SR flip-flop, set reset flip-flop, how we can find hazards and how we can make a latch. I said flip-flop, but I mean latch. Flip-flop means when we have clock, it's changed to flip-flop. So, but right now we are just in level triggered type of latches. So we are just talking about latches, no clock. And we want to see how we can design a latch that is originally by itself hazard free. It's not hazard not gonna happen in that. We can do that today. What else we gonna talk? Yeah, mostly talking about those things. Okay, so let's get started. So last class we mentioned to study actually asynchronous circuits, we always consider a delay delta, and we separate output of the circuit from the previous state of the circuit. Like we call that Y star and Y. So we said if we have a sequential circuit like this, and we have a loop that coming in, so we have some input. We set this called Y star, and we put delay delta. This is Y. So with using this delta, we kind of separating previous state from last state. So Y star is the last state. And we want to find this relationship between previous state and last state, Y star. So why this is important for us? Because in this case, we can study behavior of this circuit or latch. We can study behavior of the latch. But right now, we have two different views of asynchronous circuits. We want to talk about these two different views. One view is an algebraic view, and another view is behavioral view. So we have two views, algebra and behavior. So we have two different views for asynchronous circuits. Sometimes algebraic view and behavioral view are equal, completely equal. It means that is very aligned, but sometimes not. We can see that today. So what is algebraic equation? So normally in asynchronous circuits, we are actually finding output based off inputs using some logic gates and some feedback paths. So these feedback paths actually specify, the next previous state for us. It specifies the previous state for us. So let's see how we can actually find this y star based off actually gates. For example, you have a latch like SR latch. So this SR latch has you implemented using NOR, for example. You have two NOR, one for RS, and the feedback coming out. So this is, we put Y star here and Y here. So can you silence your microphone, please? Okay, thank you. So this is the SR latch. So we want to study this to find Y star. So we want to see how we can do that. Normally, what we need to do that, let I clean this up to explain this list, and we can have examples soon. So normally we have 4 steps. First step, we need to identify state variables. The state variables are just those y's, those loops. And then based off those state variables, we can write Boolean equations for each gate. Like for those XORs, we can find them all, and then substitute them all together to find Y star. So we can find Y star based off those, and then start to see if it's stable or not. Based off the different inputs, we can see how output change. So we can study like that. So normally we have these steps to find algebraic equation. So we're gonna see example. First example, let's look at the SR latch. SR latch is normally can be written like this. And when R and S are 0 is act as a memory. When R is 1 and S is 0 is reset, and when S is 1 and R is 0 is set. And 1, 1 is not allowed. We have one state that is not allowed. So let's find algebraic equation for this one. So to find algebraic equation, as I mentioned, we just need to use delta to specify, to separate a next state from actually previous state. This Y is, and we write the output for each gate and substitute them all together to find Y star. So first let's write here. It is gonna be, this is OR, this is NOR, so it's S or Y, not, because of this not. And then let's write this here, and then another R plus S plus Y. Oh, this actually has one, yeah, at a bar and then another bar. So if we write them up, and a De Morgan law gonna make this. So this equation is algebraic equation for SR latch. If, for example, S is 0 and R is 0 is hold. Why? Because when S is 0, this is 0, and S bar is 1, so this is gonna be Y, so it means hold. If S is 1 and R is 0, so let's see what happened in this case. S is 1, so this is gonna be always 1, and R is 0, so R bar is 1, so this is always 1, so it's set. And if S is 0 and R is 1, is reset. Because, so as you can see, S is 0 and R is 1, so this is 0, so it's always 0, so it's reset. So it works. Okay, so let's see that in a clear way. So this formula showing algebraic form of SR latch. But what about behavioral expression? Sometimes behavioral expression of latch and algebraic form are equal, but sometimes not. For SR latch is not actually, they are not equal. So how we can write behavioral latch expression? We use it with truth table. If we write a truth table for the latch, we know we have three inputs. We have three inputs, SR and Y. Y is the previous state, and Y star is the next state. So all combination of SR, Y gonna be, because 0, 0 is hold, so it's gonna be hold, so these two gonna go here because it's holding, and 0, 1 is actually reset, so these two reset. As you can see, we don't care about Y and it's always reset, and this 2 is always set, and as you can see, it doesn't care about Y and just set. This means the output is Y, and 1, 1 is invalid, so is don't care. Okay, so if we write Carnot map for that, so what we gonna get? So the Carnot map, I already have the Carnot map somewhere, I think. Yeah, I think here. So the Carnot map, let I clean this up to show the Carnot map. This is for Y hat. So we write 0, 1, 0, 0, 1, 1, don't care, don't care. Okay, if we group them together, you can make S plus R R bar Y, or complement of R and Y. Okay, so as you can see, this is not same as previous one. The previous one was R bar S plus Y. As you can see, these two are not equal. That was S bar R plus Y. That coming from actually algebraic form, and they are not equal. So how we can explain that? So normally, that makes asynchronous circuits a little complicated. So these two are aligned together as far as we consider these inputs for S and R. Both of them acting correct. We can test it. For this one, we already tested. It was okay. What about this one? Let's test this. Let's test this. If SR is 0, 0, supposed to be hold. So if it's 0, 0, y hat, y star is equal to s is 0 plus r is 1 and y, so is y, so is hold, so it's correct. If SR is 0, 1, what about this one? Y hat is equal to, so S is 0, so is 0 plus, that's 1, so is 0 y, so it's always 0. So this is reset, so it's correct too. And if SR is 1, 0, y star is equal to 1 plus, what is r? R is 0, so r bar is 1, 1y. 1y is actually y. Oh, 1, so yeah, it's set. So that's correct too. So because whatever is here, we have 1 here, so it's always y. So that's correct. So these two are kind of consistent, but algebraically are not equal. So that's why I want to mention sometimes for some asynchronous circuits, behavior view and algebraic view are not equal, but they are consistent, but mathematically they are not. These two are not mathematically equal. So you can't prove that these two are equal. But you can write same output in terms of behavior for them. Okay, let's do more example. Let's clean this up. Let's go for D-latch. D-latch is kind of simplest way of SR latch. So because this part is SR latch. And D-latch, we have clock here, but this clock, we are not triggered with the edge of the clock. Where we consider clock as another input. It's like another input. We call it C, or clock. It's like another input because we are in a level, triggered with the level, not with the edge. So this is not really clock, it's another input. And the D is actually the input that D going to, for example, this is S and R. S and D bar going to R, but we make that actually AND it with the clock and then negate it. So this is D flip-flop. Let us study D flip-flop. So for D flip-flop, so normally this is happening. If you draw this, let's draw this. We have two inputs, clock and D, and Y. We also have Y. So we can write all the combination that happening 0, 0, 0 and Y star. We have 0, 0, 1. We have 0, 1, 0 and 1, 0. Oh. 1, 1, 0. And then 1, 0, 0, 1, 1, 0, 1, 1, 0, and 1, 1, 1. Okay, this is all combination of this for D flip-flop. We have C as a clock, D as an input, Y as a previous state, and Y star as a next state. So normally D flip-flop acting like that. If the clock is 0, the D flip-flop acting as a memory. So whatever is Y is going past. Okay. And if C is 1, if clock is 1, whatever is, if clock is 1, whatever is in D passing. So we don't care about the past. We just pass whatever coming as an input. So this passing. So let's write this up as a Carnot map. If we write the Carnot map for this, we're gonna get 0, 1, 0, 1, 0, 0, 1, 1. Okay, let us clean up the rest. If we group them, so the best grouping, like the optimal way, is to make one group for CD and the other group for C bar Y. Okay, so that's the best case that, and this is the next state equation. So this is how we can write the next state equation. Is this equation actually a glitch happened in this, or if hazard happened? We're gonna see. Let's first define what is hazard. So this equation is what we had before. We are still we still don't know if hazard might happen in this and how we can fix that. But we're gonna talk about this soon. But first we need to see what is the hazard, what is static hazard, what is dynamic hazard, and how we can find hazard, how we can fix hazard. We're gonna talk about this soon. But the only thing that we wanted to mention, this is the behavioral equation for D-latch. What is behavioral? Because we write that up based off truth table. But for D flip-flop, actually behavioral and actually algebraic form are equal. We can prove that. Like here, let's see if we can write this here, like, because this is y star and we put this here and we make y in this case, and here is another for this is y star bar and y bar. Okay, so what is here? This is DC bar. This is actually D bar, C bar. Okay, so Y star is actually we also can consider this like in a NAND form, is the same, so we can write it as a NAND form to be consistent, but they are equal, or just or. It doesn't matter. Let's write it as a or. Okay, as a actually like this. We make this DC bar plus or. What is this? Y y bar, that is after that is become y. Am I right? So I think I made mistake somewhere. Let's write that again. So here we have DC. Here we have, oh, okay, I got it. Okay, I got it. So yes, that's right. So we have, because we need to replace it. Okay, that's correct. So this is y star is equal to, this is y bar, DC bar plus y bar. But y bar, you need to find y bar from this part. What is y bar? Y bar is equal to D bar C bar plus y bar. Oh, this y bar becomes y actually. This y bar becomes y. Am I right? Yeah, that's why it's better to write it as a NaN form. Yeah, it becomes a little complicated. Let's write it again. Okay, um, let's write it as a NaN form instead of this. So y a star is equal to DC bar, or with y bar, all of this bar. Okay, so this part coming from the downside, we have here this one. So how we can find that y bar coming from this, that goes again, this is equal to this. So d bar c all bar, and with y and all of this bar, and if we put this, substitute this in this, after simplification, you're gonna get that. I'm not gonna do that, but you can do that by yourself. This is gonna be similar. These two are similar. In this case are similar. In SR latch wasn't similar, but in this gonna be similar. Anyway, I just wanted to show that. It becomes a little mess, but this is how we can find algebraic form. Algebraic form is just using these gates and substitution and find that, and this is a little complex. But using behavioral is more convenient because you just use a Carnot map and actually using a truth table to find that. Okay, so right now that we know how to find behavioral equation and algebraic equation, let's go for defining what is hazard, what is static hazard, what type of static hazard we have, what is a dynamic hazard. Essentially, hazard is a glitch, something that we don't want it. For example, the output supposed to stay 0 and briefly jumping to 1, or supposed to be 1 and suddenly going to 0. That's called hazard. So normally we have two types of hazard. If we're supposed to stay in, for example, 0 and suddenly jump to 1, that's called static 0 hazard. And if we're supposed to stay at 1 and suddenly drop to 0, that's called a static 1. This is just definition, it's not important. This happened if we have a loop. Most of the time when we have one loop and one delay, we have like a gates that has different propagation time, this is happening. But sometimes we have another type of hazard that's called dynamic hazard. Dynamic hazard is when output is oscillating multiple times to get settled. In dynamic hazard, normally we have multiple paths. When we have multiple paths that they have different delays, this causes this fluctuation. You are multiple times going to 0 to 1, 1 to 0. These topics that we are talking about, like from last time and today and end of the week, mostly is advanced digital systems. So we're not gonna go deep in that. We're just gonna just talk a little bit as far as you know that this part of this kind of circuits also exists, and but later on, probably in other courses, maybe you go deeper on that. So we're not going to talk about dynamic hazard anyway. We're just going to talk about static hazard, simple case. Okay. So this is the picture that you can see. So the hazard, the static hazard, 0 when you're supposed to 0, jump to 1, glitch happening. And in static 1, you're supposed to be stay in 1, but you jump to 0 for a very limited time and come back. And dynamic hazard, you are just fluctuating multiple times. And this dynamic hazard happening when you have multiple paths. And we have different delays for each one. That's happened. Okay, so how we can fix it? How we can detect it? How we can fix it? Normally, most of the detection can happen when you're trying to do behavioral, when you study behavioral of the circuit using Karnaugh map. That's the easiest way to find it. So normally in Karnaugh map, you can check groups to see if there is some groups that are adjacent groups. Between these adjacent groups, because between adjacent groups, you have, for example, a Karnaugh map like that. Let's make it like that. You have multiple variables, and you have one group, for example, here, another group here. These two are adjacent groups because, as you can see, these variables changing in one variable. This is 0, 0, this is 0, 1, this is 1, 1, this is 1, 0. These two changing in one variable. They are adjacent, but in the group, they are different groups. This is the case that hazard can happen. So this is how we can find, for example, in this circuit, hazard might happen or not. If there is a group, there is multiple groups adjacent that they don't share any elements between them, this might cause hazard. So how we can fix it? So normally how to fix it, we just need to add another term. We just need to add another term like this, adding just extra terms, not changing anything, you know. But this extra term, later we call that a consensus term, because it's like both agree on that, can solve the problem of hazard. That's the amazing part. So this is how we can deal with hazard. Let's go deeper on that with some examples. So simply, if two adjacent cells of equal value are covered by different groups, that means hazard. So this is how we can find how do we have hazard or not. So let's explain more. So how we can fix it? We need to identify two adjacent, one hazard, adjacent 0 if you are doing product of sum. But if you are doing sum of products, just look at the ones and see if they belong to different groups. We need to add a group of 2 or 4 based off the actually what we have to cover those cells. So we can't have two groups that are adjacent and they don't have overlap. We need to make overlap between them. We need to make kind of overlap between them. And this overlap gonna solve the problem of static hazard. So this actually called consensus term. Consensus term because it's both agreeing that are this. So this is consensus term because it's one extra term that happening between these two, and normally is not optimal, but doesn't matter as far as hazard not happen. It should be okay. So let's do that for D flip-flop. Okay, for D flip-flop, we had something like that. Is any question? Let's see. Are you effectively adding redundancy to your system to order to remove hazard? Why does that works? Okay, so why does that works is because they are that's acting like a breach. Like, let's see that in this example. Let's see that in this example. Okay, let's bring that down. So here we want to see what is the consensus. What is the consensus element? So let's see what is this coming from. Let's see if I have this already here. I think so. I have it. Let's see. Yes. So in this case, so we have we add one extra element, one extra actually part dy with making the bridging these two. So when we look at the D-latch kernel map by itself, these two groups, these two green groups are actually neighbors. They are adjacent. They are adjacent. So here, these two, like as you can see in these two, they are changing in one variable. In here is C, and here is C bar. Here is C and C bar. Yes, C bar and C. So this new group actually creating an extra term to the equation that kind of smooths out the transition. So that's the point. We want to find a way to smooth out transition. Between states. So how we can smooth out this transition with adding this new term. This new term is kind of, as you can see, it has D and Y, and D and Y is existing these two as well. So if this a state's coming from Y, a state variable is Y variable. So this adding this dy is kind of a smoothing out transition between states. So if the states wants transition from one state to another state, if there is a glitch or a static hazard happening, in this case, this extra term gonna actually smooth that out, gonna remove that part. This is how it works. In other words, by adding this consensus term, so this acts as a consensus term, you were making sure that when a circuit moves from one group to the other group, there is no momentary hazard, or there is no momentary glitch. So that's the point. So the reason that we have this bridge is that we want to kind of make sure that we are changing from this group to the other group, we stay consistent. That's the reason that that we use that. So that's the whole idea. You are just adding bridging to the kernel map to cover these adjacent cells and eliminate hazard. Once you do that, the D latch not gonna have glitch anymore. Okay, so let's see how this happened for D flip-flop. So the new term for D flip-flop gonna be like that. So instead of that circuit that we had before, we're gonna have a new circuit for D flip-flop. So the new circuit has D as an input, has clock as an input, and also has Y as an input. And Y, let's consider that Y now. Okay, so how we can do that? We can find CD, one AND gate to make CD, another AND gate for C bar. Let's make C bar 2, C bar and Y, C bar Y, another one for D and Y, another one this. However, this Y is coming from that side. This is going to here, okay? And then this is gonna be dy, and we OR them all together. And this is gonna be Y star, and this is the delta delay that we have, and this is Y. And this is the new design for D flip-flop. So this D flip-flop is the hazard not going to happen in that, at least this static hazard. So this is the different design for asynchronous circuits. When we have asynchronous circuits, we need to always have a circuits that is tolerate hazards. So, and this is how we can find it. First, we need to find it. How we can find it? Using Karnaugh map. Karnaugh map is one method, like a normal method. At least in this class, we use this method. This simplest way. We draw Karnaugh map based off the behavioral of the circuits, based off the behavior. Here is just D flip-flop circuit, is not complex. But if you have D flip-flop, you can make everything with D flip-flop. And this is how we can design other asynchronous circuits. There is no clock here. This C is just as an input. We are level triggered. We are not edge triggered anymore. And actually using this consensus term is this one. This consensus term is actually kind of smoothing out the transition between states. If we are because the glitch happening when you are transitioning between a state, when you are moving from the memory to set or reset, when you are changing and transferring the state, means this Y star and Y becomes different. So in this case, when this is happening, this extra term gonna fix that out. You know, this is the reason that we are using this extra term. This extra term act as a smoothing term, act as a consensus term. That's why it's called consensus. Consensus means they both agree on that. That's the reason that we can actually say why we use that. Any other question about that? Okay, in terms of questions about these parts, I'm not gonna ask complex questions in exam regarding that. However, we're gonna have lots of examples and sample exam. I'm gonna have one sample exam for you guys soon. The final exam gonna be closed book, closed slides, and you can bring your calculator if you want. That's fine. Just calculator is allowed, but nothing else is allowed. Okay. Another thing we is lockdown browser, because for midterm 2 I realized many students, at least if they couldn't because I was there, but they tried to just do some suspicious stuff, things that I didn't like it. Anyway, exam gonna be lockdown browser, so that's why we need to test it out. Probably Wednesday night. I don't want to make it during the class time, because during the class time we can do something useful. I like to do it Wednesday night, 1 hour exam just for test. I still seeing that you didn't do survey for the class. I really need you guys to finish the survey. At least 80% of you guys, if you do that, is gonna be very helpful for me. And if you do that, I'm gonna make that exam very similar to your final exam. And it's gonna help you a lot. Anyway, that's what we're gonna do. So next class, we are done in terms of adding extra things. I just gonna have some extra examples for you guys next class. And for Friday class, I also can answer your questions if you have any questions. Other than that, we're gonna solve the exams that I'm gonna have for Wednesday. Still, I don't know, maybe I make exam Wednesday or Thursday. But please doing the class survey evaluation of the class. I want to see what I need to change if I want to teach this course again. Okay. Thank you so much. If you don't have any question, we can make it a day and see you Wednesday. Have a good day.